Okay, yeah, so welcome back, everyone, and thank you for coming back. Today, I'll continue telling you a bit about a very brief introduction to tropical ideals. Maybe what I'll start doing is doing a recap, just a second, doing a recap of what we did last time. So last time I was trying to give you an overview of the history of how this field began and what ideas are motivating it. And we saw that the main idea is that if you have a classical ideal J in a polynomial ring with coefficients in a field K, you can tropicalize the variety of J, the zero set of J, and that gives you a tropical variety. But we can also associate a scheme structure to it. So some algebraic object that encodes more information than just the variety. And we can do it in different ways. We can do it via the ideal. So just consider all possible tropicalizations of the polynomials that are in your original ideal. Or equivalently, this is the same information, you can do it via this congruence that tells you when two functions are equivalent on that variety, and it was defined, we defined it last time. And equivalent to the congruence is the coordinate semiring, which is the semiring that you get when you identify all the polynomials according to your congruence. And that's a semiring that plays the role of the coordinate semiring in tropical geometry. So these are three different algebraic objects that you can associate to your variety, and that they give you the scheme structure. So today I'm going to focus on the ideal point of view. I'm going to tell you guys that these ideals that we get by tropicalizing classical ideals, and the more general ones that we defined last time, they have very nice properties, the tropical ideals we were talking about. So I'll recall the definition because maybe it was a little bit rushed last time. We're going to say that an ideal, and now it's an ideal in the tropical semiring. So the coefficients are tropical numbers and operations are tropical operations. We say that this is a tropical ideal if it satisfies the monomial elimination axiom. So the monomial elimination axiom is telling you that whenever you have two polynomials in your ideal, if they have a monomial where the coefficient is the same, so if there is some monomial x to the u such that the coefficient of x is equal to the coefficient of g in that monomial, and it's not infinity, so it's actually a monomial that appears in the polynomials, then there must be some other polynomial in the ideal where that coefficient is infinity, the coefficient of that monomial is infinity, and all the other coefficients are at least the minimum of the coefficients in f and g. And actually, this has to be an equality if the coefficients of f and g are different. Okay. Let me open the chat just a second. Yeah. Okay, so that was the definition of a tropical ideal. And we said that the motivation is that we want to consider a class of ideals that look like tropicalizations of classical ideals. But we definitely don't want to consider all possible ideals in the tropical polynomial semiring because that's really getting out of tropical geometry. We're considering too many things. So this seems to be a class that is well suited for tropical geometry. If you have heard about tropical linear spaces, then this monomial elimination axiom is just telling you that if you consider the polynomials in your ideal of degree at most d for any d, so if you truncate your ideal at some degree d, then those polynomials must form a tropical linear space in the corresponding affine space where they live. All right, so yeah, if you have a different favorite way of thinking about tropical linear spaces, that's also a valid definition. So that was the definition of tropical ideal that we had last time. We said that the main example, as I just said, is the ideals that come from tropicalizing classical ideals, and we're calling this realizable tropical ideals. Just in analogy to matrix, for instance, realizable matrix are the matrices that come from an honest classical point configuration or point configuration over a field. But we said that we expect most of these tropical ideals to not be realizable. And in the problem session, there was an exercise about constructing one tropical ideal that was not realizable. So probably not all of you saw that problem. Let me just tell you the definition of that ideal here, just also if you haven't, so that because we're gonna use it in the mini exercise today. So the ideal is an ideal in two variables, x and y, a tropical ideal in two variables, x and y, and it's going to be generated by polynomials that look like this. So tropical sum of some monomials without any coefficient, with the coefficient equal to 0. And the condition is that the collection of monomials that you put here, that in the polynomial f, they are going to be k plus 2 monomials inside a standard triangle of size k. Okay, so what do I mean by a standard triangle of size k? I'm going to be thinking of monomials in variables, in the variables x as y, as lattice points in the plane. So I'm going to associate I'm going to identify each monomial with its exponent vector. So for example, in the origin, I'm going to think of the monomial 0, just the constant 0, which is the tropical multiplicative identity. Here is x, x squared, x cubed, and so on. And going up, y squared, y cubed. Here is xy, xy squared, and so on. So you have a whole lattice of monomials in x and y. And a standard triangle of size k is just some triangle of monomials in this configuration that looks like this: vertical, horizontal, and slope -1. So an isosceles triangle that looks like this. This is a standard triangle. Okay, something that looks like this. And then the condition is that you're gonna put a polynomial here in I.
Which is, what does
yes.
C minimal with this property mean?
Yeah, thanks. I'll get to that in a second. So the condition first here is that you need to involve k plus 2 monomials in a triangle of size k. So for instance, here is a triangle of size 1 in the plane. Right? It's a standard triangle of size 1, vertical, horizontal, and -1 slope. And I have 3 monomials in there: y, xy, and y squared. So this qualifies as one of the generators of our idea. And the thing I have here in parentheses is that C needs to be minimal with this property. And that means that whenever you remove one of the monomials from C, then it doesn't satisfy this property anymore. No subset of that, removing one monomial, has k plus 2 monomials inside a triangle of size k. Okay, so yeah, let me delete this. And here are some examples of the generators you're putting in I. So for instance, 0 plus x plus y is a generator for I because these are 3 monomials inside a triangle of size 1. Here's another generator, although you don't really need it because it's a multiple of this one, but y plus xy plus y squared, these are 3 monomials in a triangle of size 1. Here's another generator, 4 monomials in a triangle of size 2. These 4 that I have highlighted here. Here's another one, 5 in a triangle of size 4, of size 3. So these 5 monomials, the sum of those is going to be a generator of your ideal, and so on. And you have infinitely many generators. You take the ideal that they generate, and that's going to be I. So the exercise, and it's not that easy to prove, is that this is actually a tropical ideal. So that I is a tropical ideal. This collection of polynomials that I'm defining here, they satisfy the monomial elimination axiom. Okay, so for instance, if you take this y squared plus y plus xy, that's one generator. Here's another generator, xy plus x plus x squared. So this is another one that you have because it's 3 monomials inside a triangle of size 1. They share a common monomial. They share this monomial here. So there should be one way of, there should be some polynomial in there that doesn't use this monomial and uses only the other 4 monomials, and that's exactly this one that we have on the right. So it takes a little bit of tricky combinatorics to prove that that's always going to be the case, that this collection of polynomials satisfies the monomial elimination axiom, but it does, and then I is a tropical ideal.
So we have a question, do you fix the size k?
No, so this has to, this is, you put a generator for all k. So it might be 3 monomials inside a triangle of size 1, or 4 inside a triangle of size 2, or 5 inside a triangle of size 3, and so on. And all of those are going to be put as generators of I. Yes. So that's the ideal. It's a tropical ideal. And now the claim is that this is not a realizable tropical ideal. And that's not so hard to see. Let me show you why. So suppose it was realizable. Let's say I is the tropicalization of some classical ideal J. Let's say J has some coefficients in some field K. Then, well, here in I you have the tropical polynomial 0 plus x plus y, that has to be the tropicalization of something in y, in J, sorry. So there has to be some polynomial in J that uses the monomial x, the monomial y, and the constant monomial. You can actually, without loss of generality, you can assume that that polynomial is just x plus y plus 1. So you can scale the whole polynomial so that this constant coefficient is 1. And then you can scale the variables, which is not going to change the support of your polynomials. It's not going to change the tropicalization. So that the coefficient of x is 1 as well, and the coefficient of y is 1 as well. So we don't lose generality by assuming that x plus y plus 1 is in J. But then if this polynomial is in J, all multiples of it have to be in J. And in particular, this carefully chosen multiple, if you take x plus y plus 1 and you multiply it by this quadratic polynomial. So here the coefficients are chosen specially so that there's a lot of cancellation happening when you expand this out. And then what you get at the end is x cubed plus y cubed minus 3xy plus 1. So this would be forced to be in J, but let's see, well, x cubed corresponds to this monomial here. Y cubed is this top monomial here. Xy is this monomial in the center. And 1 is the constant monomial. Then the tropicalization of J would be these 4 monomials. But these 4 monomials are too spread out. There are 4 monomials that are not really in a triangle of size 6. They're of size 2, I mean. They're 4 monomials that live in a triangle of size 3. And that means they don't classify as a generator, or they're not generated by these polynomials. So this is a contradiction because you end up with a polynomial that you will be forced to have in the tropicalization of J that is not there. Okay. So yeah, in the exercise, I explained this with more care, but are there questions about that? Do triangulations of product of 2 simplices give such set C? That's a good question. I don't see it right now how they would, but I learned about these collections of sets coming from a paper from Cerebellum and Federico Ardila investigating flag arrangements of subspaces and the matrix that they can form. And this is the matrix they describe that they form. Maybe there's a connection there with the product of simplices, subdivision of product of simplices, but I don't see it right now. Does this only show it is not a generator? Yes, it shows exactly that it's not a generator because it's too spread out, but it's also not, like anything that you generate with these polynomials has to have that property of having some monomials that are packed together, that it has to have k plus 2 monomials inside a triangle of size k. Even the ones that are not generators, but generated by them, because there is no cancellation that you can make with them, then that property is preserved under taking the ideal generated. And because these 4 guys are too spread out, then they are not in the ideal generated by them.
And do you see above that, why aren't we forced to have an element with 0x, y squared, xy?
Why aren't we forced to have an element 0x, y squared, xy? Well, 0x, y squared, xy. So that would be a generator, I think. Yes, yeah, that'd be a generator. That's another, I'm not listing all of them here. So you're right, there's another one that consists of 4 monomials inside a triangle of size 2, and that would be y squared, xy, x, and 0. That's valid. That's a collection of 4 monomials inside a triangle of size 2, and it's minimal with that property. As soon as you remove any of the 4 monomials, you get 3 monomials that are too spread out. They don't fit in a triangle of size 1. Yeah. Excellent. So this is one example of a non-realizable ideal. It was hard to construct. Somehow it was not so obvious that such ideals existed, but our expectation now is that most tropical ideals look like this. They're not generated by, they're not the tropicalization of a classical ideal. Okay, so that's basically what we did last time. And then today what I want to tell you a bit more about is that this is a nice definition. This is a useful notion that has a lot of nice properties that are desirable for algebraic geometry and for tropical geometry. So one way of thinking about it is that, remember, in tropical geometry, we don't have minus, we don't have negative additive inverses, but this elimination axiom sort of makes up for the lack of that additive inverses, okay? So you don't have negation, but there's a way of taking two polynomials and canceling monomials that they have in common if they have the same coefficient. And that takes you a long way and allows you to prove a lot of things that hold classically. Maybe the first thing you have with this definition is that there's a well-defined notion of Hilbert function. So Hilbert function for a classical ideal just measures the dimensions of the different, let's say you take a homogeneous ideal, classical ideal, then the Hilbert function of that ideal measures the dimension or the codimension of each of the homogeneous pieces of the ideal. Right? What's the dimension of the polynomials of degree 2 in your ideal? What's the dimension of the polynomials of degree 3, 4, and so on? And that function is the Hilbert function. So you can do the same for tropical ideals. The Hilbert function of a homogeneous tropical ideal, so now this is an ideal over the tropical semi-ring satisfying this monomial elimination axiom. You can define it as the function that takes some degree and spits out a dimension, or a codimension in this case. So if you input the degree d, it's going to be, the output is going to be the codimension of the degree d part of I. So these are polynomials of degree exactly d, inside the space where they live, which is the space of all polynomials, all possible polynomials of degree d, which we are identifying with r bar to the monomials of degree d. So what do I mean by codimension here? The thing is that because we're requiring that ID is a tropical linear space, it's a tropical linear space by definition. Tropical linear spaces are very well-behaved polyhedral complexes or combinatorial objects or geometric objects, and they have a very nice notion of dimension. So for example, if you think about them as polyhedral complexes, they are pure polyhedral complexes of some dimension, and that's the dimension. That's the notion of dimension we want to use here. So here, well, yeah, the codimension in this case. One way of defining that more combinatorially, more matroidally, is this codimension is going to be equal to the size of a maximal set of monomials of degree d.
We have a question here about the definition of ID.
ID is, yes, I changed, ID here is degree exactly equal to d, because I'm assuming I is a homogeneous tropical ideal, so it has a degree d part. And that's what I'm taking here. So this is degree equal to d. Okay, yeah. Thanks. You're right, yeah. I should have said that this also satisfies elimination. So because it's a homogeneous ideal, then, well, the definition for it was saying that polynomials of degree at most d was a tropical linear space. But because it's homogeneous, this decomposes as the sum of different linear spaces, one for each degree, and therefore that's why I can say just degree equal d, and that's a tropical linear space. Yes, thank you. So I was saying that the codimension you can define combinatorially as the size of a maximal subset of monomials that does not contain any support of any polynomial in I. Okay, so this is what in matrix we call a basis, a maximal independent set. Meaning that here independent means that it doesn't contain the support of any polynomial in your ideal. In the exercises, you're going to prove that all such maximal subsets have the same cardinality. The monomial elimination axiom implies that all maximal subsets that do not contain the support of a polynomial, they all have the same cardinality, and that's the codimension. All right. So I should say that this notion that we're defining here of Hilbert function for a tropical ideal, that agrees with the notion of Hilbert function for classical ideals, in the sense that if you take the tropicalization of a classical ideal J, then the usual Hilbert function you have for the classical ideal, which is just measuring the codimension of the ideal inside the polynomial ring, that's just the same as the Hilbert function we define here for the tropicalization, right? So in some sense, this notion is extending the notion of Hilbert function for classical ideals to the non-realizable world as well, of non-realizable tropical. So first good thing is we have a very nice notion of Hilbert function for ideals. And then in this paper with Diane from 2017 or something, we proved that this notion satisfies a lot of nice properties. For instance, just like for classical ideals, in classical ideals, whenever you compute this Hilbert function, it turns out that for large enough d, this is actually a polynomial in the degree d. Okay? At the beginning, you might see some noise, but after some point, this function is actually a polynomial in your degree D. That also happens for general tropical ideals. That also happens for the non-realizable ones. Okay? So for any tropical ideal, this Hilbert function is eventually a polynomial. And this polynomial, well, we can call it, as in the classical case, the Hilbert polynomial. Hilbert polynomial of I. All right. So this is a very useful invariant of an ideal, of a homogeneous ideal. It's Hilbert polynomial. Something else that we can prove using these ideas of Hilbert functions is that, well, remember we had these examples that tropical ideals are usually not finally generated. You usually need infinitely many generators to describe them. Even for the very simple ones, even if you take a binomial, like a classical ideal that is generated by one linear binomial, we saw that when you tropicalize it, you need infinitely many generators to generate it. So we cannot expect, these are not finally generated, but if you restrict to the class of tropical ideals, then that class satisfies the ascending chain condition, meaning that you cannot find an infinite ascending chain of tropical ideals in the tropical polynomial summary. Each of these guys is going to be infinitely generated, typically, but you cannot keep going on forever and continue satisfying this monomial elimination axiom. At some point, you have to stabilize and just repeat the same polynomial over and over, the same ideal over and over. All right. So this is very good news. This is something that we really like in algebraic geometry, to have a notion of finiteness for inclusions like this. That's what allows us to define dimensions of things, and tropical ideals allow us to be in that realm. All right. So let me tell you a bit of how these things are proved. Just very quickly, the key tool that we use there is initial ideals. The key tool that we keep using over and over to discover new things about tropical ideals is initial ideals. So I think the first week we talked about initial ideals for classical polynomials. How if you take, for classical ideals, if you take a classical ideal and you pick a weight vector, how that defines an initial ideal. Well, we can mimic the same thing tropically for tropical ideals. So let me do that here. Let's say you have a homogeneous tropical polynomial now. So some tropical sum of tropical monomials with their tropical coefficients here in front. And you pick, let's say it's homogeneous. So yeah, and you pick some weight vector that you can think of assigning a weight to each of the variables. So it has n+1 coordinates because there's n+1 variables here. Then this weight vector defines an initial term of the polynomial. And the way that initial term is just going to be, you pick out the monomials appearing in your polynomial where the term has minimal weight.
We have a question about this slide. Which
yes. Does this mean there are finitely many elements that, together with monomial elimination, generate the ideal? Yeah, I would like something like that to be true, but the problem is that monomial elimination is not a deterministic thing. So monomial elimination tells you that if you have two polynomials that have a common monomial, then there exists some other polynomial that where this monomial in common is infinity. And there's some condition about the other polynomials, but it doesn't tell you what that polynomial has to be. There's many possible choices you could choose for the elimination. So it's not possible to say, take these polynomials and generate using monomial elimination. You have to make a choice of what the eliminations are going to be. And those eliminations need to be compatible in some sense. So yeah, this is one of the questions that I have at the end. I would like to have some procedure for describing an ideal like that. Start with this and then maybe eliminating some minimal weight possible or something. I don't think we have that in general yet. Great, thanks for the question. So yeah, so the initial ideal, the initial term of a polynomial is just pick out the monomials corresponding to terms of minimal weight. And the weight of a term is just the coefficient plus the dot product between the exponent and the weight vector. So basically, it's you evaluate the tropical polynomial as an affine, as a piecewise linear function in this point W, and the monomials that achieve that minimum, those are the ones you record in the initial term. Yeah. So that's how you take the initial term of one polynomial, sorry. But you can define the initial ideal of a whole ideal, of a whole tropical ideal I, just by, well, the initial ideal of I is the ideal generated by all the initial terms of all polynomials in I. And you can just take the homogeneous ones if your ideal I is homogeneous. Okay? So this is just mimicking the theory of initial ideals we have for classical ideals. The key fact that makes a lot of things work is this actually matroidal fact. This is a fact about matrix, saying that if the ideal you start with is a tropical ideal, if this I that you take is a tropical ideal, then its initial ideal for any W in R to the n plus 1, that's also a tropical ideal. And actually, if you follow the combinatorics along, you realize that they have the same Hilbert function. The original ideal has the same Hilbert function as the initial ideal. This is something that happens classically, and it happens tropically as well. And here is just a purely matroidal fact, if you unravel the definitions. All right, so we have a way of sort of simplifying our ideals by taking initial ideals that allows us to deform our ideals to something simpler and preserving this property of being tropical and of having the Hilbert function. Can you recall the geometric interpretation of taking initial ideal? Yes, so geometrically what you do is you're taking a sort of a Grobner degeneration of your ideal. You're scaling the variables. You have a torus action acting on your variables, and the torus action is given by the weight vector that you choose. And then what you do is you take the limit as the action goes to infinity or to 0, and that's how the variety deforms tells you what the initial ideal is going to be. Yeah. Can the initial ideal also be defined for non-homogeneous ideal? Yes, yeah, absolutely. You can also define initial ideals for non-homogeneous ideals in the same way I'm doing here. Yeah, that makes sense. And yeah. Does the weight need to be rational then? Yeah, that's a good point. Maybe if you want to have this, if you only want to deal with polynomials that have integer exponents or rational exponents, then you want your weight vector to be rational. But if you're willing to deal with polynomials that have real exponents in general, you can allow real weight vectors. Yeah. Thanks. So maybe let me tell you how. Remember, we had this. Wait, where's my pen? We had this theorem that tells you the Hilbert function of a tropical ideal is eventually polynomial. And I want to show you how to use initial ideals, how to use this notion of initial ideals and this key fact to prove this theorem. So the idea is the following. The idea is basically, so suppose you take a tropical ideal I, any tropical ideal. You want to show that its Hilbert function is polynomial. Then what you do is we can pick a double. So choose W so that initial ideal is a monomial ideal. I claim that if you pick a very generic W, then the initial ideal of I is actually going to be a monomial ideal. Why is that the case? Well, the tropical ideal is, we said that tropical ideals are not finally generated, but they're definitely, if you stand at some degree D, there's finitely many polynomials that generate that degree. Okay, and then what you want to do is you want to pick a W that for each of those polynomials, its initial term is just a monomial. So it picks out a single monomial in each of those terms for every degree, right? So you see that if W is generic, then there's only going to be one monomial that achieves the minimum in a polynomial, and that means the initial term of a polynomial is going to be a monomial. And if you have a finite collection of them, or even an accountable collection of them, which is what we have in this case, I is generated by a countable collection of polynomials. There's finitely many for each degree. Then all you have to do is to pick a very general W that picks one single monomial from all of those countably many polynomials. And that ensures that the initial ideal you get is only generated by monomials. So it's going to be a monomial ideal. is the geometric statement that you can degenerate to a union of coordinate planes. No, I don't think that's true.
Yes, for a monomial ideal, yes.
For a monomial ideal is the case, yeah. Yes, yeah. In general, the initial ideal is not. Oh, I see. Yeah, in this situation, yeah. Okay. Yeah, if the initial ideal is a monomial ideal, the variety is a union of coordinate hyperplanes. That's right. And then, so take a very general W that deforms your variety. Although here we don't really have a variety. This is we're even including the non-realizable case. But so take a very general W that whose initial ideal is a monomial ideal, and then, well, this fact is telling you that you still preserve the Hilbert function. When doing this, the Hilbert function of your original ideal is the Hilbert function of this monomial ideal. But a monomial ideal, it really doesn't matter if it's tropical or classical. They have the same Hilbert function. So yeah, how do I say that better? If you take the classical ideal generated by the same monomials that generate your tropical ideal, they're going to have the same Hilbert function, because the Hilbert function is just measuring which monomials are divisible by your generators, and divisibility is the same classically than tropically. So the classical theory tells us that this monomial ideal, even though it's a tropical monomial ideal, well, it behaves as if it was a classical monomial ideal, and therefore its Hilbert function is eventually polynomial. Eventually polynomial by the classical theory. And actually, you only need to use the fact that Hilbert functions of monomial ideals are eventually polynomial to prove this. All right? Does it mean that it becomes realizable? Yes. So this degeneration is going to be realizable. Every monomial ideal is going to be realizable, but the original one is not. So here we might be taking a degeneration of a non-realizable tropical ideal into a realizable tropical ideal. That's right. Okay. And good. So yeah, are there questions about this? So it becomes very simple to see that the Hilbert function is eventually polynomial once you know that this is preserved under taking initial ideals, because you can deform to a case where you know that it's going to be eventually polynomial, a monomial ideal. So I had planned to tell you guys a similar argument for why we can prove the ascending chain condition also by degenerating by using initial ideals. I'm not going to write anything down, but because of time, but let me at least tell you verbally. So how do we prove that every infinite ascending chain has to stabilize? Take an infinite ascending chain of tropical ideals, choose a very generic W so that the degeneration of all of them is a monomial ideal. That you can do because there's only countably many conditions that you want to avoid. So then that degenerates to an inclusion of monomial ideals. And because monomial ideals behave like classical ideals, then you know that this, and the ascending chain condition is true classically, then you know that this chain of monomial ideals has to stabilize. That means that those initial degenerations, at some point, they're all the same. And that means that they have the same Hilbert function, because Hilbert function is the same after degenerating than before degenerating. Then you know that in your original chain of tropical ideals, at some point, the Hilbert function has to be constant, has to be the same. And now it becomes a fact of matrix theory to prove that if you have two tropical ideals of the same Hilbert function, one included in the other, they have to be equal. And that's true, that's a fact of tropical linear spaces. Two tropical linear spaces, one included in the other of the same dimension, have to be equal. Okay. So yeah, I'm sorry, I'm not gonna write that down, but just because of time, but hopefully that was a bit clear.
We have a question from the previous slide, I think.
What's a monomial scheme which is a degeneration of the ideal given in the example? I'm very glad you asked this, because that's the mini exercise after this session. So the mini exercise is going to ask you guys to compute initial degenerations of the non-realizable ideal we had at the beginning. And yeah, I can tell you the answer. So actually the initial ideals for that non-realizable example we had are the same as the initial ideals of the tropical line, the standard tropical line, x plus y plus 0. Okay. So for example, just the ideal generated by x is one monomial ideal, or just the ideal generated by y. Yes, so the mini exercise is already in Piazza, and we'll make it available. So it is possible that all these initial degenerations it's possible for two different tropical ideals to have exactly the same initial degenerations, except at the origin, for instance. That's what happens with the realizable line and the non-realizable line that I've shown. So hopefully that's more clear with the exercise. I explained also better there. And then maybe the last thing I want to say about initial ideals is that you can construct the Grobner complex of a tropical ideal in the same way you do it for classical ideals. What you do is you partition the space of possible weights, the space of possible W's, meaning you partition R to the n+1 according to, so you put two W's in the same cell if the initial ideal if the initial degeneration they define, if the initial ideal they give you is the same. So the cells of the Grobner complex correspond to the possible initial ideals of your tropical ideal. This is mimicking the definition we have classically, and in fact, if you take a tropical ideal that's the tropicalization of a classical ideal, then this way of defining the Grobner complex for I gives you the same polyhedral complex as the same complex as the Grobner complex for J, as you defined it classically. We can also prove using these ideas that even for non-realizable tropical ideals, the Grobner complex is always a polyhedral complex, a finite polyhedral complex, okay? So you're always gonna have only finitely many possible initial ideals, and they fit nicely in a polyhedral complex that we call the Grobner complex. And the mini exercise is gonna ask you to compute the Grobner complex of that non-realizable tropical ideal. That's not as difficult as it sounds because the ideal has very simple generators in low degree. So we have Grobner complex. We have initial ideals for tropical ideals. We have a Grobner complex, which is a finite polyhedral complex, just as classical ideals. That's all very good news. This we all like in tropical geometry. And now let's move on to discuss varieties of tropical ideals. Remember, we're very interested in the varieties, in the vanishing locus, the tropical vanishing locus of these tropical ideals. Well, from this point of view of initial ideals, you can see that the tropical variety, or the variety of a tropical ideal, is just going to be a subcomplex of the Grobner complex. It's going to consist of some of the cones of this Grobner complex. The Grobner complex partitions all of Rn, or Rn+1 if your ideal is homogeneous, but the tropical variety picks out some of those cones. It picks out exactly the cones corresponding to initial ideals that have no monomials. Remember, the variety is telling you, the tropical variety is the condition that for every polynomial, the minimum is attained at least twice. And that just means that the initial terms of all the polynomials, they're never a monomial, they're only binomials or more. And that's exactly the condition that the initial ideal has no monomial. So it's a subcomplex of the Grobner complex. Could you please provide some references for these lectures? I definitely will, yeah. Please remind me at the end and I'll post that link with all the references. Yeah, and Chihu is already giving you some. So what I'm telling you guys about right now is in a paper with Diane called Tropical Ideals from 2018 or something in the archive. Yeah.
There's a request to say what a Grobner complex is.
Yes, so the Grobner complex, let me go back one slide. The Grobner complex is just this. It's just, I'm not defining it completely precisely here, but it's a polyhedral complex where two points are in the same polyhedron if the initial ideal, so W is in the same polyhedron as W prime if the initial ideal given by W is the same as the initial ideal given by W prime. So each ideal has a Grobner complex associated to it. And it's given by this condition. The cells correspond to equivalence classes of weights where two weights are equivalent if the initial ideals are the same. Yes, thanks. I can draw an example, but I don't want to draw the example in the mini exercise. So if I is equal to the tropicalization of x minus y, then, well, there are two variables. So the Grobner complex is going to be a subcomplex of R squared. And what we're going to do is we're going to put together weight vectors if they give you the same initial ideal. So in this case, you see that there's three possibilities. If x is greater than y, so W is going to have two components, W1 and W2. If W1 is greater than W2, then the initial term you're going to pick in this generator is going to be y. It's going to be the one with smallest weight. That's the variable y if W2 is less than W1. So to the left of this line, to the down of this line is what I'm talking. Here, the initial ideal is going to be y. Okay, so for every W that you pick on this bottom half, in this bottom half space, the initial ideal with respect to the W is going to be the monomial ideal generated by y. But if you now pick one here where x is less than y, then the initial ideal, well, in this generator, you're going to be picking the monomial x now instead of y. And it turns out that the initial ideal that you pick is just the ideal generated by x. So all of this is another cell of the Grobner complex. And there's one more cell, which is this intersection of the two pieces. In this cell where x is exactly equal to y, then the initial term of x minus y is, well, you pick both of them. It's just, I'm going to write it already tropically. I don't want to say, let me just say it's equal to I. Even though that's not completely precise, but you pick both of the, you pick x minus y as the term, the leading term. So in this case, the Grobner complex is going to have three cells, two maximal dimensional cells corresponding to these half spaces, and one-dimensional cell, which is where they meet. And that's the Grobner complex corresponding to this tropical ideal. Yeah. And in the exercises, you guys are going to do one that is slightly more complicated, but not too much. Okay. Good. So varieties of tropical ideals. We discussed that the variety of a tropical ideal is a subcomplex of its Grobner complex. In the example we just drew before, let me go back one slide. The tropical variety for this ideal is actually just this line where the minimum is attained twice, where the initial ideal has no monomials. You discard this one because here the initial ideal has the monomial x. You discard all this side because here the initial ideal is just contains the monomial y. But this part in the middle, the initial ideal has no monomials inside. It's generated by this binomial. So that qualifies as part of the tropical variety. And that's the tropical variety, the variety of this tropical ideal. So it follows, because the Grobner complex is a finite polyhedral complex, it follows that the variety of a tropical ideal is always also a finite polyhedral complex. It's a subcomplex of this complex. So this is something that we very much like in tropical geometry. Remember, one reason for not wanting to deal with all the ideals in the polynomial semi-ring is that their varieties could be very strange, non-polyhedral objects, curvy objects. It turns out this is showing that if we restrict to the class of tropical ideals, the class of ideals with this monomial elimination axiom, we recover this fact that we like about tropical varieties, that they're combinatorial, they're finite polyhedral complexes. And if you investigate a little bit further, you'll realize that, in fact, any tropical ideal contains finitely many polynomials that cut out the tropical variety, the variety already. So the variety of I as a set is just the intersection of the hypersurfaces, of the tropical hypersurfaces, determined by all those finitely many tropical polynomials in I. So that's what we call a tropical basis. They exist for realizable tropical ideals. We knew that already, but this is showing that even for non-realizable ones, you can always find a finite collection of them, a finite tropical basis. Something else that we didn't like about all the ideals you could have in the tropical polynomial semi-ring is that they didn't satisfy the Nullstellensatz. Well, if you restrict to this smaller class of tropical ideals where the monomial axiom is satisfied, you recover the weak Nullstellensatz. So in this setup that I have here, where the variety is a subset of R to the n plus 1, the Nussschellen says that the variety of a tropical ideal is empty if and only if I contains a monomial. Okay? So basically, if you have a collection of tropical polynomials in such a way that there is no way of choosing a W that picks out at least 2 monomials from each of them, then it's because there's actually one certificate, there's actually one monomial in that ideal. And of course, it's impossible to pick more than, it's impossible to not pick a monomial as an initial term if the polynomial itself is a monomial. But yeah, okay. Yeah, so this is what the Nussschellen says. This is analogous to what we have in classical algebraic geometry. The variety of an ideal in the torus is empty if and only if the ideal contains a monomial. Right? So we recover the weak Nussschellen. All these theorems that I've told you are in this paper with Diane called Tropical Ideals. And then let me tell you a bit, a bit more about what we've been investigating more recently. We're still interested in understanding these varieties of tropical ideals better. We know that they're finite polyhedral complexes, but we want to know more. We want to know their dimension, for instance, or if they have more interesting properties that we are used from tropical geometry. Well, remember that tropical ideals have a well-defined Hilbert polynomial, which is the polynomial where the Hilbert function stabilizes to. And that polynomial has a degree. Classically, that degree is measuring the dimension of the variety of the ideal. So let's just mimic that definition, that classical definition, and say that the dimension of a tropical ideal now, maybe a non-realizable one, is just, let's define it as the degree of its Hilbert polynomial. This we still haven't posted in the archive, but this is a very recent theorem that we're still finalizing the writing of. And it says that also tropically, for non-realizable tropical ideals, that's the case, that the variety of a tropical ideal is a finite polyhedral complex where the cells that have maximal dimension have exactly that dimension given by the exponent of the Hilbert polynomial. All right. So the Hilbert polynomial is a very useful invariant. Its degree, even for non-realizable tropical ideal, tells you the dimension of the variety of the ideal. Okay, so that's one recent development that we have. Also, for tropical varieties, we're used to this notion of the balancing condition. I think we wouldn't classify a polyhedral complex that is not balanced. We wouldn't say that that's a tropical variety. We like our tropical varieties to satisfy this zero tension condition around every cell of codimension 1. You can define multiplicities for maximal cells in the variety of a non-realizable tropical ideal, or of any tropical ideal. You can define multiplicities on these maximal cells. And for a while, we were wondering if those multiplicities make it a balanced polyhedral complex. So this is another recent development that we still haven't posted, and we're still finishing the writing of. And it's that it does. These varieties of tropical ideals, it doesn't matter if they're realizable or not. They come with multiplicities, and the multiplicities on the maximal cells make it a balanced polyhedral complex. Okay? So something like this, where the maximal cells come with some weights, and the weights, if you pull from those faces with that strength, the thing here in the middle doesn't move. Okay? They satisfy the zero tension condition. Something we don't know how to do is, in this structure theorem for tropical varieties, for the realizable ones at least, you know that if you start with an irreducible classical variety, then the tropicalization, the polyhedral complex that you get as the tropicalization, is a pure polyhedral complex. All the maximal cells have the same dimension, equal to the dimension of the original variety. Tropically, it's not so clear what irreducible means. So one open problem that I would suggest, that I'm very interested in, is to find some kind of useful algebraic or combinatorial property that you can impose on a tropical ideal that ensures that its variety is pure, that all the maximal cells that you see have the same dimension. Okay, so you would want some kind of way of saying that the tropical ideal is prime but it turns out that the naive notions of prime do not work so well. Can we do all this in projective tropical space? Absolutely, yes. We can in fact do it inside any tropical toric variety, toric tropical variety. So in particular in projective space and in tropical projective space we can do it, and that's also in the paper Tropical Ideals if you want to know more about it. So maybe the last thing I want to say is that, well, I've told you some very nice properties, that tropical ideals satisfy, that we like them a lot for doing tropical geometry, and we see that they really do behave as if they were tropicalizations of classical ideals, even if they're not realizable. They share a lot of common properties. But there's a lot of things that we don't know yet, and there's a lot of research directions that we would like to pursue. So for instance, we know now that the tropical varieties, the varieties of tropical ideals, are always balanced polyhedral complex. How about the other way around? Is it true that every balanced polyhedral complex is the variety of a tropical ideal? This is related to the question I was asking, the issue I was mentioning last time, that we would like a theory that includes non-realizable varieties, that includes polyhedral complexes that maybe look like a tropical variety in the sense that they're balanced, for instance, but maybe they're not the tropicalization of anything classical. Can we still find some non-realizable tropical ideal that has that variety? Can we give a scheme structure to these non-realizable varieties? For a while, we didn't know if this was true or not. Now, in a paper with Jan Drijsma, we showed that actually the answer is no. There are balanced polyhedral complexes that you cannot give a scheme structure, even if you include non-realizable tropical ideals. So one of them, if you know about Bergman fans and tropical linear spaces of matrates, one of them, the one we could find, is you take the Bergman fan of the direct sum of these two matrates, the Vamos matrate and the uniform matrate of rank 2 on 3 elements. So this direct sum ends up being a matrate of rank 6 on 11 elements. And that means this is a 6-dimensional polyhedral complex in 11-dimensional space that is balanced because it's the Bergman fan of a matrate. So some combinatorially defined polyhedral complex, 6-dimensional polyhedral complex in 11-dimensional space. We proved that there is no way of making that the variety of a tropical ideal, even if you allow non-realizable ones. And the thing that fails, the thing that makes this impossible, is actually some classical theorem in matrate theory related that shows that it is not possible that a tensor product for matrates exists. There is no notion of tensor product for matrates that creates an impossibility here for an ideal having exactly this variety. So the answer is no. Not every balanced polyhedral complex is the variety of a tropical ideal. But there's still an open problem that I'm very curious about, and is, well, maybe are there any whose variety is a non-realizable tropical variety? So far, we know there's several non-realizable tropical ideals, like the one I gave you at the beginning of this talk, but their varieties are still realizable. Their varieties, for example, the variety of the one I showed you at the beginning is still the tropical line, the realizable tropical line. We still don't know of a tropical ideal whose variety is some non-realizable tropical variety, some non-realizable polyhedral complex. So I wonder if that's possible or not. One possible way of attacking this is there a tropical ideal whose variety is just the Bergman fan of the Vamos matrix? So here we show that there is no tropical ideal whose variety is the Bergman fan of the Vamos direct sum with this U23, but maybe is it possible to remove the U23, and is there maybe one that gives you the Bergman fan of the Vamos matrix? This we don't know. We don't know if here exists or not. Many tropical ideals correspond to the same space. Yes, yeah. So you can have different tropical ideals, all of them with the same variety. That's very possible. And then that's also the case. That's a useful that's a useful point of this theory. You want to have different scheme structures that you can associate to the same set. Sometimes you want to think of the tropical line as just one tropical line. Or maybe you want to think about it as a double tropical line with the same set, but maybe you want the functions that vanish there to require that they have to vanish double or triple or so on. And that's that you want in a theory of schemes. And that happens here. You can have different scheme structures for the same tropical line. There was an open question mentioned about tropical ideals whose varieties are not pure dimensional. This open question suggests that there is not yet an example of a tropical ideal whose variety is not pure as a realizable tropical variety is pure. Is this correct? No, so there are tropical ideals whose variety is not pure, and that happens if you start with for example, with a classical ideal that is not prime. If you start with a classical variety that has different components, that have several components, maybe one 3-dimensional component and one 2-dimensional component, then its tropicalization is going to have a 3-dimensional component and a 2-dimensional component. So we can definitely have tropical ideals that have non-pure varieties. But what we know is that if the classical ideal is prime, if it's irreducible, then the variety has to be pure. And we don't know what tropical condition is saying that the tropical ideal is prime or irreducible. That's what we're looking for. Yes, yeah. If you record multiplicities, then it is unique? No. So in fact, the non-realizable ideal, so is the scheme structure unique even if you determine multiplicities? No. The non-realizable tropical ideal I gave you at the beginning, its variety is the tropical line, and it still has the same multiplicities of the tropical line, meaning 1, 1, and 1 on the 3 cones. So it is not, the scheme structure is definitely more information than the set and the multiplicities. How do you think of this extra scheme structure? That's a good question. The ideal is telling you this structure, but you don't really see it geometrically. That's the point of scheme theory. You really do need to deal with the tropical polynomials themselves. Is it a coincidence that the variety and the initial ideal of the non-realizable example and the ideal of the tropical line are the same? Well, it's not really a coincidence, and hopefully in the mini exercise it's more clear why it's not a coincidence. These ideals are very similar. They differ only in high degrees, but in low degrees, which are the ones that determine the variety and the multiplicities, they are the same, and that's why they end up being the same. They just differ high enough, but you don't see that in the variety and the multiplicities. Yeah. Okay, let me try
There was one more question about, which maybe you can answer in 2 minutes if you'd rather, the notion of a radical ideal.
Is there a notion of radical ideal? No, there is no notion of a radical ideal. So one thing you might try is you start with a tropical variety and you consider all tropical polynomials that vanish in that variety. It turns out that that's not a tropical ideal, for instance. Or you could also require just a naive definition that if the power of the polynomial is in the ideal, then the polynomial is in the ideal. That also doesn't produce tropical ideals. It doesn't satisfy this monomial elimination axiom. So that's a very good open question, I guess, to come up with a good notion of radical ideal. Yeah. Okay, so another research direction that I would really like someone to pursue is to develop commutative algebraic results for tropical ideals. One bad thing about tropical ideals is that they're not closed under sum or intersection, for instance. If you take 2 tropical ideals and you add them, you might end up with something that is not a tropical ideal. Or if you take 2 tropical ideals and you intersect them, you might end up with a tropical ideal that is with an ideal that is not a tropical ideal. It doesn't satisfy this monomial elimination axiom. And in the exercises tomorrow, you'll have to give examples of this. It's not hard. So I would like to have some way of, even it's not the set intersection or the regular sum, but some way of adding tropical ideals or some way of intersecting them. We don't know, something that is useful for doing commutative algebra on these ideals. That's still to be developed. As I said, there is no notion so far of what a prime tropical ideal should be. We don't know what a primary decomposition for these tropical ideals should be. We don't know what a free resolution should be. All these are things that are very useful when you do algebraic geometry, but they're missing so far for tropical ideals. So this is something that we're really looking for. And then the last thing, I'll say that a possible research direction is to, well, the way I'm describing tropical ideals here is they're a a collection of polynomials, but this collection can be infinitely generated. And in fact, the information is encoded by an infinite sequence of matrices. No? The matrix, the tropical linear space corresponding to polynomials of degree 1, degree 2, degree 3, and so on. And you need, and in total, you have infinitely many degrees, infinitely many linear spaces. How can I finally describe this? How can I email you one tropical ideal? And we don't really know. And I was going to give you some example that I'll skip this slide, but there is an example I learned from Alex Fink that tells you that even if you restrict to just ideals with a very simple Hilbert function, so ideals in one variable with Hilbert function 1, 2, 2, 2, 2, so meaning ideals that correspond to a double point in the origin, there's a lot of them, and they actually, the space of those tropical ideals looks like a Berkovich line. I'm not going to explain to you why this is the case, but it turns out that there's a lot of them, and this looks like a Berkovich line, the ones we were discussing last week, in the sense that there's like, it's an infinite branching tree, and at every point in the tree you have countably many branches, and at each of those branches you have countably many branches, and so on. That's what the space of tropical ideals with corresponding to a double point in the origin looks like in projective one-dimensional space. So there's a lot of tropical ideals, and we would like to describe all of them in some way. We don't know how to do that. So yeah, maybe I'll stop here. Thank you.
So thank you, Felipe. I know there's already one question, but maybe we should start by, please join me in thanking Felipe for a very nice talk. And then I think Yusuf's question was, is there a way to take an arbitrary ideal and make it tropical in some nice way?
Yeah, this is related to the question at the beginning that I think Dan was asking. Is there a way of describing a tropical ideal by giving you some polynomials in there and then saying, okay, then just close them under monomial elimination or something like that? It's not that simple, because when you want to close under monomial elimination, you need to make choices, and the choices are not canonical. There's not a canonical choice you can make. So I don't know. I'd love to. This is related to defining what the sum of tropical ideals is. What should be the tropical ideal generated by two polynomials, for instance? And that's like the sum of the tropical ideal generated by this one and generated by that one. How do you add them together and say it's the tropical ideal generated by the two polynomials? We don't know how to do that. So another open question there. Very, very good. Yeah. Is there a theory of quotients? So, for example, does every congruence come from the bend relations of a tropical ideal? No. So, yeah, that's a good question. Bend congruences of tropical ideals are very special. You can define the bend congruence of any ideal, even if it's not tropical. But the bend congruences for tropical ideals are very special. And in fact, the quotient semirings, the coordinate semirings that you get, they're very special as well. And actually, this is something that I feel should be more studied. We haven't thought about it so much. What special property does these coordinate semirings satisfy? How can you distinguish them among all the possible quotients that you can make from congruences? How do you distinguish if one of these is a tropical one or not? And yeah, that's a very good research direction there. I agree. Yeah.